Hello, welcome to the back. This is the PLTW's POE, Introduction to Structural Member Properties. That's a big fancy way of saying we're going to look at beams. This is going to be in Unit 212. So now what we're going to be doing is we're going to be talking about structural members. First off, structural member is a beam of any kind whatsoever. So looking at we can look at the right here, we can look at our diving board. And we got to first talk about moments of inertia. Moments of inertia is the mathematical property dealing with how the cross-sectional area looks like and how this weight is distributed over its axes. It deals with how stiff an object is. In general, a higher moment of inertia produces a greater resistance to deformation. So let's look at this joist. So can you notice how the joists or these beams are actually situated? They're situated in a way that's cross this way, along this way. Why didn't they flip them the other way? Okay, so now we look at this. We got a joist versus a plank. The difference is they're exactly the same material, same everything, weight, length, height, and area. The only difference is one is sitting in the plank version where the longer side is up while this one's the shorter side. This is called a joist. This is referred to as the plank. So what distinguishes them both? It's just by changing their deformation. Now if we look at this animation, we can actually see that as a plank it bends more. So what you can do is just by changing its orientation can change the overall inertia, the moment of inertia due to that. So the way we do that is by calculating the moment of inertia. The base times the height cubed divided by 12. Notice the cube is going to have a greater impact than the base. So I want you to do that for this beam. Alright, we put it in 1.5 times the 5.5 cubed divided by 12, and then you put that in, that gives you 21. Now do that for B. Again, same equation, but this time 5.5 times 1.5 cubed divided by 12, and that gives you 1.5. Huge difference of deformation. You can actually see that both numerically and in the animation. So you can also do this for composite materials, looking at a square beam versus an I-beam, and they are drastically different. But notice the area, this is stronger than the I-beam, but the overall area is significantly less and uses a lot less material. So an I-beam is significantly stronger for using the less material. Now, a modulus of elasticity, or E, is how related specifically it's stress over strain, and it defines how stiff material is. So it's dealing with the material, not the shape. So we can look at, compare plastic versus a Douglas fir, wood versus plastic. Everything's the same except for one is made out of plastic, one's made out of wood, and the plastic, as you would suspect, bends more, and that's because of the modulus of elasticity. And its defect, how much it bends, determines based off of that modulus of elasticity. So that amount of bend, how much it bends down, its delta max, is its force applied times the length that the beam is, divided by 48, divided by the modulus of elasticity. This will be given to you. It's a number for every chemical, and everything in the universe has one, times, again, its moment of inertia. So we put that in for this beam, and we get 0.12 inches, so only just a tenth of an inch. Do that for the plastic, and we get a half an inch deformation, using the same amount of weight of 250 pounds of somebody standing on it. So you can see that it's 4 times less deformation. And if you have any further questions, go ahead and ask your teacher.